Hello! In our first video lesson, we discussed how PyMAPDL can be used within a web app to bring sophisticated simulation insights into the hands of many people. In the prior lesson, a basic web app of a mechanical APDL model was described along with a short description of each part of the web app. Now we will choose a specific mechanical APDL model and start to develop the backend to a fully functional web app based on this model. Ready? Let's get started. Please take a minute to download the lesson file package and extract it to a location of your choice. The extracted file set should look like this. vm35.py is the PyMAPDL Python file that we will be using as the example model. This file is the APDL input file of the mechanical APDL verification model number 35 converted into PyMAPDL format. The goal of this lesson is to turn this into a Python module that will be saved to the lib folder per good Python and Flask practices. The MAPDL working directory folder will be used for the MAPDL working directory, though we will change the name later to better reflect the actual PyMAPDL model. The static folder will contain the CSS file and any static images we create. For example, the result contour plot image will be saved here. An image file of our example is already included. The templates folder will contain the HTML file. Lastly, app.py is a skeleton Python file with Flask implemented to process the PyMAPDL model and present the web app webpage. The mechanical APDL verification manual example number 35 was chosen for this example. As we can see, this example comes from an external reference book, which happens to be one that many mechanical engineers have. Therefore, it is a good idea to note this on the web app page and perhaps plan on implementing the reference calculation as well. You may want to open the image of this example in the static folder previously mentioned or take a screenshot to have on hand. Here we can see the list of material, geometric, and loading properties of the example. The existing PyMAPDL input file has these hard-coded. We'll need to change these to be parameters whose values the user sets in the web page. You may want to take a screenshot of these as well. Moving over to the included PyMAPDL input file, we can see that the file ends after the solution. All post-processing will then need to be created. Before we start editing the PyMAPDL input file, let's take a quick look at the app.py file. We can see that this is a basic framework of the application. An empty function exists that will call the PyMAPDL script to create the working directory, starts the mechanical APDL as a service instance, then processes the model's input file. Some yet as to be determined results will be returned. Here we can see that some inputs will be passed, mainly the example parameters as shown here. Back to the vm35 Python file. Let's start by reviewing the file, as there are some PyMAPDL and APDL commands that those new to PyMAPDL may not be familiar with. Starting with the three styles of comments. /com and C*** both add the comments to the mechanical APDL output file, with the C*** version adding C** to the line, making it easier to find in the output. The exclamation point style comment annotates the input, but it does not echo the comment to the output. The title command adds text to the mechanical APDL plots. Here it is the description of the model, so we could add the title information and reference to the web page. The sec type and sec data defines the section data for the specific element type. The model uses a multi-layered 8-node shell element, and the section commands define each layer's thickness and material model reference ID number. The style used to create the finite element model is a direct generation of the nodes and elements instead of creating geometry then meshing the geometry. The end command defines a node with the node numbers and then the XYZ positions. The fill command creates a line of nodes between two nodes. Then the E command directly defines an element based on the nodes in the specific order. Generally, when changing a model's input file to be parametric, it is a good idea to keep in mind the necessary mesh to accurately capture the results given the geometric parameters. In this model, 5 elements are enough to be accurate for a large range of length, width, and thicknesses, so the direct FEM generation will be kept. Otherwise, it may have been a better choice to create the area and mesh it with sizing based on the dimensions. TREF sets the reference or strain-free temperature for thermal expansion, and BF uniform sets a uniform body force on all selected nodes. In this structural analysis example, temperature can be applied as a body force. Okay, I think that covers the PyMAPDL commands, so let's look at our list of parameters that entered the file. We will work our way down the list of parameters, so first the length is set in these two end commands for nodes 22 and 11. Each layer is half the thickness, which we set here in the secData commands. Next, let's add the material parameter for both materials, replacing the values here with the parameter names. And lastly, we can replace the temperature values in the TREF and BF uniform commands with the parameter names. That completes the changes necessary for the parameters, so let's move down to the Python with command that initiates the solution. The /out redirects the output, which is a normal part of the verification examples but is not needed here. Let's take out the with and the /out commands. PyMAPDL native result plotting commands plot with the nodes in their initial locations. Here we prefer to show the display shape in any result plot, and we'll be using a PyMAPDL result plotting command. We can add the upchord command in the solution block with a value of 1, which is a scaling factor. This will add the displacements to the node locations. Moving to the results, the strip will bend such that the free end displaces in the z direction. Depending on the input thermal expansion coefficients, the bending could be in the positive or negative z direction. We can capture a plot of this bending with a maximum z displacement, given that it could be a positive or negative value. Let's add the commands to enter the post1 processor and read the last set of results. Next, we'll use a Python OS module command to join together the path to the folder containing the image and the image name. I am cheating here a bit as we not yet defined the path images, but we will keep in mind that this will need to be passed to the script in the function call. The scalar bar key arguments are defined to give a title with black lettering, orientated horizontally with 9 values in the legend. A z nodal displacement plot is then issued with an isometric view, a white background, using the prior scalar bar definition, and saving the image to the file defined with PNG path. This next command returns a numpy array of the nodal z displacements. Max is a Python command and will return the maximum of the array's maximum or minimum given the absolute value, but the sign is kept on the return value. The processing of the model input file is complete, so we end by exiting out of the mechanical APDL instance. Next, let's scroll back to the beginning of the file. The Python comment can be deleted. And we use the OS module, so let's import it. And now the PyMAPDL script can be changed to a function excluding the import and the creation of the MAPDL instance. The image path and MAPDL instance will be passed along with the input parameters. A folder to use as the MAPDL working directory already exists, so let's create a function to clean the folder of any files. Here, the OS module function can be used to create a list of files in the folder, then loop over that list and OS remove the files. Now, let's create a function that launches the MAPDL instance. First, it should create the working directory if needed. Otherwise, cleans it with the folder cleaning function we just created. Once that is done, we should launch MAPDL with the run location set to the working directory folder. We can pass in the job name to use. And given the small size of the FEM, one CPU core can be used in shared memory parallel mode. At this point, we can implement the result given the reference solution. From Works 7th edition, the equation of the maximum Z displacement is given by this, and K1 defined by this. Note that in our example, the two layers thicknesses are equal, so the expression simplifies a lot. Let's create a function for this, taking a few steps to make it a bit easier to read, passing in the same inputs, and return the values rounded to the 3 decimal places. Now, let's save the file with a more appropriate name to the lib folder. In fact, let's save it to its own folder in lib. Okay, that was quite a bit of work. Let's end by creating a file of often used constants and saving it to the lib folder. As we go along, we can add constants, but here I've cheated and have included all those that will be used. There are 2 used to launch MAPDL, the working directory, and job names. One that defines where to store images and one that stores the result image name. Then 2 that will be used as messages to the user. This concludes the video. Please join me in the next lesson where we wrap up the web app by reviewing the HTML and CSS files, complete the Python script, and test the web app with some varying inputs. See you there.